Hi, I'm Hannah.
Hi, my name is Coral.
Hello, my name is Raga Shiram.
Hi, I'm Luca.
Hello, my name is Geeta Gachaturi, and we are Carmel SWENext.
With the overall goal to detect colored plastic in the ocean, there were requirements for several of the subsystems. Regarding the payload, the camera had to take the appropriate amount of images, which is why we plan to create software that allows the capture mechanism to activate every 20 seconds. The communication subsystem needs to allow access to the data collected, which is why we plan to create software which allows the CubeSat to transfer all data and images to the ground station during the communication window during orbit. And finally, all systems need to remain operational for the entire duration of the mission, which is why we will continue to ensure that the hardware is assembled correctly and conduct several tests to confirm proper functionality. Additionally, the CubeSat will conduct scans at frequent intervals to overcome any errors found.
So the first thing that our team did for the concept of operations is essentially actually booting up the systems and checking them. This is done through looking at the structure subsystem, the power subsystem, the payload subsystem, the command and data handling one, the communication, the altitude determination and control. All of these subsystems were systematically checked. Once they were checked, we turned on the avionics to make sure that this was active. Once this all was a success, we moved on to the next stage, launching it into orbital operations. However, if there was an error detected, we would send this information back to the ground station so that these subsystems could get checked once again to see what was causing this error. Moving on from the launch into orbital operations, it'd be put into orbit insertion. Once that is successful, it would move on to the self-testing of the functional systems. However, if there's an error in the self-testing of the functional systems, this would go to the ground station once again. The ground station then would once again look at what is causing this error. And during this time, if there is an error, it would try resolving it and sending it back to once again the self-testing of the functioning system. However, if the error is not resolved, it will lead to a change in the mission as the ground station would not be able to actually fully answer the problem of the self-testing of the functioning system. During this time period, the communications is active. Assuming the self-testing of the functioning system is actually is active and actually functioning, this leads to a success where the active systems will all be turned on. And because of that, the science mission will be conducted and the orbits will be adjusted for the mission so that the CubeSat can actually do its function during this time period. In addition, the ground station will keep on relaying communication and the CubeSat will be relaying the communication so that the self-testing of the functioning system can still tell us if there will be a potential error when it's doing its mission.
This is our systems level block diagram. It consists of our structure subsystem, which includes our acrylic structure as well as the aluminum rails and connectors used to connect the acrylic structure together. And then we have our power subsystem consisting of our solar panel and our power bank. And the solar panel is used to charge our power bank, which then powers the Raspberry Pi, which is on our command and data handling subsystem, which also includes our SD card, which is used to store data from the Raspberry Pi. And we also have a payload subsystem, which consists of the Raspberry Pi camera. And the Raspberry Pi camera, the data that it records is stored on the SD card for the Raspberry Pi. And then we also have our attitude determination and control subsystem consisting of our IMU, and the data collected from the IMU is stored on the SD card on the Raspberry Pi. And then lastly, we have our communication subsystem consisting of our ground station, which interacts with our Raspberry Pi using a Bluetooth connection. This is the CAD model for our CubeSat. Here you can see we have our Raspberry Pi, our IMU, our power bank, our solar panel, and our Pi camera. As far as wiring is concerned for our CubeSat, we're going to have a USB cable connecting our Raspberry Pi to our power bank, jumper cables connecting our IMU to our Raspberry Pi, a cable connecting our Pi camera to our Raspberry Pi, and a USB adapter board connected to our solar panel, which will also be connected to our power bank.
This is our bill of materials. We have our product, quantity, kit, and estimated cost, which was found from these links. The total estimated cost is around $290 or $300. Next, we have our mass budget. We have all the components listed on the left over here. They're categorized by the subsystem, and then we have material, what it's made out of, manufacturer or product number. And then over here we have the quantity, mass, and total comp mass, contingency, total plus contingency, and then the subsystem mass up here. So the comp mass was found by multiplying the quantity and the mass, and then total plus contingency was found by multiplying these as this formula shows over here. This was repeated for each of the subsystems. And we can see our total down here, and a 1U CubeSat, which is what we're making, has a weight restriction of 1.3 kilograms or about 3 pounds, and we are still underneath it, so we have room for adjustments if needed.
This is our power budget. We calculated that under normal conditions, our solar panel only produces 0.218 watts per hour. Under idle conditions, the Raspberry Pi uses 3.23 watts per hour. When it's processing data and taking pictures, that amount of power required increases to 4.58. So because of that, we need a solar panel that is 21 times larger to ensure proper power supply across the entire CubeSat. And so the components that we used to determine this calculation was the Raspberry Pi, the IMU sensor, and the camera.
At any point, the CubeSat will be in one of the three states shown: wait, which is when no major process is occurring; operate, which is when the image is being taken; and transmit, when the images and other data is being transferred from the CubeSat to the ground station via the Bluetooth connection. After finishing either transmit or operate actions, the CubeSat will return to wait. It'll return to transmit whenever the CubeSat is within the 600-second communication time. If it is not the 600-second communication time, then the CubeSat will turn to operate in 20 seconds. Because of this, the CubeSat is able to take an image every 20 seconds constantly, unless it is transferring data to the ground station. The first step in our software development process is to outline the specific tasks that are necessary to achieve the overall goal, which is detecting colored plastic in the ocean. We will determine each software system's roles based on the resources available to us. Then we will create a general design of the software system which will perform these tasks and how they interact with each other. After that, we will develop software in the Python language to coordinate different interactions between software systems. For example, we will develop software for the capture mechanism so that the camera will become active and take images at certain intervals. We will also develop software for the Raspberry Pi to transmit data to the ground station through a Bluetooth connection during the 600-second communication time.
This is our link budget. By calculating the signal-to-noise ratio, we can quantify the link between the satellite, so in our case the CubeSat, and our ground station, which in our case is the central hub or our computer. And so to do this, we require a value. We require these values: the uplink and downlink frequencies, satellite antenna gain, satellite transmit power, noise temperature, and that for the ground antenna as well as the bandwidth and the distance that our CubeSat will be orbiting. And so this is our link budget. And the first step to determining our signal to noise ratio was calculating the effective isotropic radiated power, how much power the satellite itself has. So for uplink, this communication is basically between the ground satellite, so the computer, and the CubeSats. And so to calculate that, we took the the transmitted power of the computer, and then multiply that by the satellite antenna gain. And that gave us 723 decibels. From there, we calculated the free space path loss. And then after calculating that, we used those two values, so the effective isotropic radiated power and the free space path loss, to determine the received power of the CubeSat. And so this value was then divided by the system noise power to calculate the signal to noise ratio, which was negative 0.921 decibels. The same process was repeated for downlink. And during downlink communication, it's the CubeSat communicating to the ground station. So again, we calculated the effective isotropic radiated power, we calculated the free space path loss, and then from those two values, calculated the power received. In this case, this power received would be of that of the ground antenna, and then we divided that by the system noise power to calculate the SNR, which for downlink is 0.94036 decibels.
This is our data budget for our CubeSat. We estimate the orbit time to be about 2 hours, and then for there to be 10 minutes of communication per orbit. Our downlink and uplink were calculated from our frequencies and our link budget. Our Raspberry Pi can take images with these pixel specifications, and there are 24 bits per pixel. This is just a bit to gigabyte ratio, and this determines how often we take our image. So right now it's set to every 10 seconds our CubeSat will take an image. The bits per image are the same for both the uplink and the downlink. The downlink is much faster in transmitting the image, as it only takes about 0.2 seconds, while the uplink takes 1.5. Well, during the communication time, we can transmit 133 photos, and this is the amount of images that can be taken in one orbit minus the 10-minute comm time. This is it in bits, and this is it in gigabytes. Obviously, we don't have enough storage, as we only have a 32 gigabyte SD card. So we'll have to increase the amount of seconds to 30 or maybe even 25 seconds or 20 seconds to optimize our storage to the amount of pictures that we can take. So here we only take up 8 gigabytes of storage if we take a photo every 20 seconds. This is the amount that can be transmitted during the comm time in one orbit. We can transmit 65.7 gigabytes during the 10-minute period. While our storage cannot handle this much, this just means that we have a lot of time during our communication time to downlink any of the stuff, and we can probably take more photos to increase this number so that we can optimize the amount of pictures that our CubeSat takes. And it's just replicated for the uplink. We estimate our housekeeping data files to be very minimal, around 4 gigabytes.
So for our integration and test plan, team members will complete their assigned subsystems. Once they've completed them, we'll work together to integrate these subsystems. So team members will basically be adding their own individual parts into this full system test. Once we finish this, we will work on issues between these subsystems that may arise. After that, we will deploy our CubeSat. So here's an integration and test flow for our CubeSat system. And essentially, we start with the structure subsystem. So we will use both of these materials, the acrylic structure and the aluminum corner rails and connectors in that subsystem. And then we would move on to this power system. Through the power system, we would create these solar panel and USB adapter boards, which would actually lead to our power bank. Once that power bank is good, we will go to the command and data handling subsystem, where we will focus from using the SD card to actually get to the Raspberry Pi. From the Raspberry Pi, we're actually able to access our 3 other subsystems: the communication subsystem, the altitude determination and control subsystem, and payload subsystem. Through our Raspberry Pi, from the command and data handling subsystem, we are able to access the ground station, the IMU, and the camera and case of the Raspberry Pi itself. So this is just the integration and test flow on how we plan to actually put everything together.